So let's talk about systems of linear equations and let's talk about what we have did so far. What did we do so far? First we started with normal Gaussian elimination. And then we said let's write down that in a little modified way. Let's decompose the matrix, the coefficient matrix A, as a product of L and U. L is a lower triangular matrix and U is an upper triangular matrix. So we can easily exchange the right hand side B and we don't have to do the whole calculation again. That was the motivation for the LU decomposition. Then we learned that there are problems if the entry left top is close to 0, and then we found out that we have to look for the largest entry in the first column, and let's exchange that row with the first row, and then let's use the entry at the top left to kill the entries below to make them 0. And so we had LU decomposition with column pivoting. And then we learned if we have entries in the left top block which are close to 0 and we have a right hand side, and if we multiply the whole equation, so that means the top rows with a large factor and also the right hand side, that does not change mathematically, does not change the system. It's only a different way of writing down an equation. You can multiply an equation by 5 and nothing happens. The solution will all stay the same. The problem will also stay the same. So multiplying a line with a factor does not change anything, but it does change if we do column pivoting. And instead of doing column pivoting, learning that, we should better do total pivoting. And that's what we did, and then we got rid of problems we had so far. Okay, what was our focus on? Our main focus was reliable, correct results, and it was easily possible to make the algorithm ridiculous. It produces wrong results, and then we improved, but then again we were able to let the algorithm produce ridiculous wrong results. But when we did total pivoting, we did not get any more ridiculous results, but the time for execution was a little more, and that's also what we want. We want fast algorithms. We don't want to spend 30% extra time if it's not really necessary. Okay, that's what we did, and that's what our focus was on. Okay, if we have an algorithm, how can we know if the solutions are correct? There are 3 ideas to do that. The first one is a very common way every professional code. When I was working for Allianz Insurance, we had a system to administrate our contracts, and if we did any change in the code, then we ran our code with, let's say, 100,000 sets of data, and then we tested what was the result before and what is the result after our change in the code, and then let's list every difference so that we, being the programmer, can find out if the algorithm, the change in the algorithm, will alter only what we intended to alter, or if we altered also things we did not want to alter. And so we found that out by that. So keep a set of problems, let's say 100,000 problems, and we know what the solution should be. And then we can test our algorithm for that set. And then we learned everything is like we intended to be. And then after that, we say, okay, let's use our algorithm now. And then we really deal with real life problems. And then we trust the solutions because we are pretty sure that there were no bugs and no incorrect code lines. So one more thing, maybe you're working on image processing, and then every 10th of a second you have to analyze an image, and it's very close to the image we had last time, and the situations are, maybe you are always on a street, and so you have very similar situations. and then you can work also on a set of these similar situations and then test your algorithm. I'm pretty sure that in your future life, in your business life, you will also be in contact with that concept. Okay, that is concept 1. Concept 2, in our special situation, having a system of linear equations, then we can reformulate that by that, very easy, and then we can examine the result of that. We apply our algorithm and then we get x, and after having that x we can multiply a by that x and subtract b, and this should be 0, but it will not be exactly 0 due to rounding errors, so it will be close to 0, and that's what we can test. It's not so easy to write professional code to test that, because sometimes we're in the situation where the entries of x are in between of 1 million and 1 billion, and then testing that difference, deviations of 1 is not so much. And next time maybe we're in the situation where x and b are entries between 0 and 0.001, and then we should modify our testing close to 0. Okay, I don't want to go too much into detail. Okay, that's our second idea, how we can test our solution which our algorithm told us to be the solution. And now the third idea is, let's use two maybe completely different algorithms, and then let's calculate the solution of a linear system. And if the two solutions are very close together, again we have the question, what is very close together? Sometimes a distance of 1 is not very much if the entries are between 1 million and 1000 millions, and next time a deviation of 1 is very much. So okay, but if they are close together, then we can be pretty sure that this means that these two solutions are correct. The mathematical logic here is, if the two solutions were incorrect, then it's completely impossible. Probability is close to 0. Two solutions calculated with completely different algorithms can't be wrong. If they are very close together, that is a very good indication that it must be the correct solution. So we can test like that. If they are not very close together, that means then at least one of these solutions are incorrect, but we don't know which one, and maybe both solutions are incorrect. We can't know. It's impossible to know which one is correct or not if we use that concept and we are not in this situation here above. Okay, so this last concept is motivating the following. It is important to know several strategies to solve a problem, and that's what we will do in the further context. We will talk about new concepts to find a solution of a system of linear equations. Okay, let's use completely different ideas. And what did we do so far? The ideas were not very different so far. We had one idea, it was Gaussian elimination, and then we reformulated or did little improvements, really little improvements, and so we went on from Gaussian elimination to LU decomposition, and we ended with LU decomposition and total pivoting. The next thing we will do is doing the QR factorization. A basic concept of the QR factorization is the same as we had at the LU decomposition, but now there are also big differences. So to really understand the QR factorization, I think it makes sense to recap the basic ideas of LU decomposition, because understanding that we can better understand the QR factorization, because some ideas of LU decomposition we will use again. And what will we use again? we have the problem A times what is B. A is a given matrix, B is a given right hand side, and what we are looking for is the vector X to satisfy the equation. And A is a square matrix. In the whole context of that script, A is always a square matrix. Okay, what did we do? Write A as a product L times U, and what is the idea, what is the concept, what is the property we can make use of? The property is, if this was the problem L, a lower diagonal matrix and a given right hand side, then it's easy to find the X satisfying that equation by forward, or in this case backward substitution. And also the second matrix of the product L times U, also here having equations like that, U times what is B given U given B, and we are looking for X satisfying the equation, then it's also easy to find the solution X, in this case by backward substitution. And that's what we will reuse doing QR factorization. So that's what we did so far, and that's what we will do next. And I hope that gives you a little overview to better understand what's following in the next videos.